This is a controller. With a nice looking front end and an absolute trash can of a backend, it lights up when turned on and displays the pixels depending on the direction the joystick is facing. Now, even though this controller is simple, in today's video we'll go over the plan, the code, the electronics, the electricity, the mechanical and design choices, and even the assembly compromises that are all made in order to finish up here. And so with that in mind, let's get started with the idea. That's because in order to build anything, we first need to describe it, and here's how we'll do it. What we have is an 8x8 pixel screen like this and a joystick. Now this joystick can move up, down, left, right, and each of these pixels can be either turned on or off. What we'd like to do is create a system in which as you move the joystick around, we want the screen to react as so let's get to work. First, let's start with the 8x8, or to be more exact, let's label these points. The thing is, there are a lot of ways to label these points, for example in lines, or maybe with a single continuous line, or maybe with a single fancy line, or maybe with two numbers each. The point is there are a lot of ways to label these points, so which one will we use? Well, as you've seen, we'd like to have these rays come from the middle, which means that the best ways to label them would be probably like this, where they are going in a cycle. So how do we do it? Well, let's start with the coordinate system that programming likes most, Cartesian. What this basically means is that you have the x and y coordinate. The more right you go, the higher the x, the more up you go, the higher the y. Now if we add them together, we can paint in a square like this, where this bright part right here is highly positive x and y, and this dark part right here is highly negative x and y. And yes, it's so dark because it's actually negative brightness. Blender is awesome. Now each line here basically represents an angle from this line on the right, and so how do we get that angle? Well, if we start with each point having its own x and y coordinate, then what we can do is a little bit of mathematical witchcraft by dividing x by y and taking the arctangent. This is what it looks like. Angles, rotations, and stuff like these would really be a topic for another time, but the point is, as we rotate, the brightness is decreasing. If not for this jump right here. You see, this jump will cause problems because it means that a point right here would have the same value as a point right here, which is undesirable because all points on these lines would have the same value, when this line is what we actually want. So what we need to do is offset the other side, and I could explain it, but I just finished a video about combining math functions, so I'll just skip this part. And so there. Now instead of visualizing it this way, I'll add a number here and just select all the points that are similar to this value. And here, we've got the thing. Great. Now we can use this exact same mechanism, but instead of doing it continuously, we can assign it to points, like this, and there we go, we've got the rotation. Now what about the joystick? Well, for the joystick, we can use the same exact method to get the same exact value, and there we go, we get the points based on the joystick. Next, there is the That was actually much easier than I thought. Okay, so here's the code I made, and I won't go in depth over how it works because everything interesting I've already covered in the first segment. But still, there's one question that's way more interesting than you think, and that's, why did I do it on my laptop? And the answer is, I didn't. Well, I mean, okay, I coded it on my laptop, but in this case, I'm using my laptop only as a keyboard, screen, and a power supply, because the actual code is running on this. That's the ESP32S2 Mini, the microcontroller we'll be using. The actual purpose of it will be explained in the next chapter, but for now, all you need to know is that this microprocessor is wildly different from my actual computer big boy processor, and as such, the code for the two of them would be different. Normally this really doesn't matter all that much for simple things like what we're doing today, but still useful to keep in mind. And now that we've gone through this, let's map our code in a way that's a tad easier to follow. Right here, I'll represent it with these connectors, and so let's examine it more closely. At the end we have the display 8x8 function, into which we plug in the generate pixel function, into which we plug in the distance and the get rotation function, into which we plug in the x and y and an empty 8x8 array. Okay, I know it's a lot, but let's get through it step by step. First we start with our 8x8 array. Then we continue by indexing all the elements of our array so we can describe each number with two different numbers, a kind of x and y if you will. So now that we've got that, we move the array into our get rotation function, and right here we plug in the x and y into the get rotation function, which results in the number of rotation. We can do the same thing for our array, this time taking the coordinates, subtracting 3.5 from them and plugging them into the function. Why subtract 3.5? Well, it's because if you imagine our array as a field, then here's where it will be equal to 0 in x and y respectively. If we subtract 3.5 from it, however, then the 0 moves to the center. Now obviously this isn't a field and these integers are there to index the elements of our array, but the math works out, right? So now if we plug it all into our generate rotation function, our array changes from an empty one to one that looks like this. And with the value as the brightness, you can see that it looks just like our rotation thing, which is a good sign. Next we take both the array and the x and y number and move on to the next stage. In this stage we're trying to achieve the individual pixels, and the way it's done is pretty simple. We take our rotation number generated by the x and y, we compare it to the array we already have, and so right here we're going to switch the array into representing the distance from itself to the rotation of x and y, and there. In order to get the pixels, all we have to do is just take the second thing we inputted here, the distance, and check if our array is greater than the distance. Now as we increase and decrease the distance, the amount selected changes. And as we move to the last function, all we do is just switch it to an O and X and just print it to the terminal. And so there, we've got all the functions. And to just go over it again, to simplify, here's our program this time in layers. First we start with an empty array and an x and y coordinate. Next we plug them all into a generate rotation to get the array of rotation and the rotation value. Then we use this rotation value to create another array, this time telling us the distance from the rotation on the right. Then we take this array and create another from it, this time with an additional value, the distance value. And so the idea is simple. If this value right here is smaller than this value right here, then just set it to 1. Otherwise, set it to 0. Simple as it could be. Now you can see that when I lay all of these arrays down, changing the initial values is changing the array at the end, as changing the distance is changing how many values we have, and that's the point. Now what we do in the last function is we just display it on the screen like so. And as you can see, the arrays I just created don't align perfectly with the separate functions, so why did I divide it into functions in the first place? Well, it's because right here we're displaying the 8x8 on the screen, but in the end we'd like to display it on the matrix. So what would we need to change in our code in order to make it work with the 8x8 pixel screen? Well, nothing. All we'd have to do is just get rid of this function at the end, responsible for displaying it on the laptop screen, and replace it with a function that displays it on the 8x8. Same goes for the joystick at the very beginning. Just replace the values with the joystick X and Y, and the program is finished. Now all we need to do is just take care of these two. So electronics. Right here is where we'd get familiarized with our components, the ESP32S2 Mini, the 8x8 matrix, and the joystick. Starting with the ESP. The ESP is a microcontroller and its purpose is simple. You program it in some way and this program can control the pins. These pins can provide a binary output like a 1 or a 0, an analog output, so some kind of voltage, and then the inputs. A logic input and an analog input. Now the whole point here is that the microcontroller works to combine our code with hardware. Which means that if we, hypothetically, had some kind of program that could control an n×8 matrix, and if we, hypothetically again, we had some kind of 8×8 matrix waiting to be controlled, then we could use the microcontroller to bridge the gap. So how would we do it? Well, first let's talk output. As I mentioned, our microcontroller can send a binary output. So, for example, we have our microcontroller with the pins. Now we select a certain kind of pin and set up a loop. This loop would restart and run forever with a single if. This if on the inside will turn the pin on if it's off. If it's on, it will turn it off. Simple as it could be. Now if we let it run, this is what the pin value is going to look like. Yeah, I do believe that the way I described it might have been unclear, but this representation should be simple enough. It just keeps going forever and ever, looping, changing the value of our pin. That's neat. But the important thing to remember here is that this is just a number inside our software. So how could we use it to turn our LED on or off? Well, we could do it by using a microcontroller which will output actual physical electricity based on the value of the software. And so this software can control the hardware like so. Lovely. Now with input it works in the exact same way, except we're going backwards. So for example, if we add a button like so, and then power it, then we can plug the other side back into our pin. Now using the microcontroller we can create another function which just checks if there is a voltage at this pin. And now as we press the button, it lets electricity through, which means that our function returns a 1. And so that's the purpose of a microcontroller. It just turns a software value into a hardware result. And so with that in mind, how would we display something on the 8x8 matrix? Well, first let's take a look at those pins on the 8x8. We have here, in order, VCC, GND, DIN, CS, and CLK. So what do all of these cryptid messages mean? Well, starting from the left, first we have the VCC and GND, which effectively just means voltage and ground. On our ESP we have different pins designated specifically for voltage and ground. So all we need to do is just connect them and there, first thing taken care of. Next we have the DIN, which is just the data input. So here's where we'll transmit all of our data. In this case I really messed up because if I just finished the next video in the computer science series before this one, I could just link you there and you would understand exactly what I'm about to say, but instead I just need to oversimplify. So this is the basic idea. Imagine for a second that you have a simple display like this, capable of displaying numbers. Now you'd like to display something like a 9. How would you do it? Well, in binary, a 9 looks like this, 1001. So if we have a single wire connecting the two, what we'd like to do effectively is just transmit it like so. 1, 0, 0, 1. There we go. Congrats, now we can move any kind of series of numbers using a single wire, and since everything can be represented using numbers, we basically can just move any kind of information. So going back to our 8x8 matrix, we powered it and now we can input the data into it. Neat. But there is a problem. So swiftly going back to our screen, you have to remember that these two things are effectively disconnected and possibly out of sync. Meaning that instead of mapping it like we did so far, let's create two different sets of numbers transmitted. So the first one will be for our microcontroller that's transmitting the data, and the second one will be for the screen that receives it. Okay, simple as it could be. Now why does that matter? Well, it's because, as I mentioned, they are disconnected. So what if our screen will try to receive the data twice as quickly? Well then, even though we input 1001, the screen will receive 11000011, because it's reading twice as quickly. So how will we fix it? A simple way to fix it would be just add another wire, the clock wire. This wire will go high to low, to high, to low, to high, to low, and so on, so forth. Now this hardware component can be made to only read something once the clock switched between the states, and congrats, it's no longer out of sync. So going back to our 8x8, this CLK here stands for clock for that precise reason. It allows our 8x8 to figure out when the data changes. And then the last one, CS, chip select, which in this case isn't important, but basically if we had multiple screens, we could just connect them together and have them function as a grid. And so with that in mind, we can connect our 8x8 to the ESP. And now we can just do a bunch of boring, irrelevant MicroPython stuff, plus this one file from GitHub, and there we go. Now I can select certain pixels and light them up from my laptop. Neat. Now it's time for the second component, the joystick. For the joystick, it's even simpler. We've got 5 pins, and once again, 2 are voltage and ground, and 3 are coordinate in X, coordinate in Y, and button press. So now all we have to do is just get the input from the joystick back into our function, and just plug it as the X and Y coordinates. And that's why breaking it into functions previously was so important. It's because right now we can just plug it in and that's it. That really is the entire thing finished. So for example, if we select only one pixel on the 8x8 and we plug in the joystick position as the X and Y, then this is what it will look like. Simple as it could be. But in our case, we don't want to plug it in directly, only we want to plug it in to the program we created so far, which results in this. And so there we go. That's the finished thing so far. You can see now that as I move the joystick, the 8x8 changes accordingly. What's more, I also added the press joystick button. And so every single time I press the joystick, it changes the distance value from before. Which means that right now I can not only move it, but I can also press the joystick and change the spread of what we're moving. But there is still more to do. Okay, so electricity. Now, originally here I was going to just make our circuit battery powered so we could get rid of our cable, but there is a problem. You see, normally I upload a new video every 5 days, but this week has been quite tough for me. And as such, I kind of weren't able to focus on the video making quite as much as I'd like to, and I'm already on day 9, And so yeah, the problem with a battery is that normally right here you put a circuit to regulate it in some way to make sure that you don't burn your microcontroller, and I don't have any circuits that would regulate the power in this way, and in the past I have fried a bunch of microcontrollers, so instead of that we'll just keep the wire because I just simply cannot afford the delay of burning the microcontroller. So instead of adding the battery, we'll just keep the wire, and I'll just mention the fact that we need to switch our setup from this to this. That's because this joystick works by increasing and decreasing the resistance, which basically translates to changing the output voltage. And okay, think about it this way. We have our joystick into which we input the voltage. When the joystick is down, the full voltage is going through. As we move it up, less and less voltage is passing. Now we measure this and it tells us where the joystick lies. But if our starting voltage is different, then the output will be different as well, even though the joystick position didn't switch at all. And that's why we need to switch from 5V VBus to a 3.3 on the other side, to keep the output consistent and keep it centered so that when the joystick is in the middle, we get the right voltage. And so there, I've already done it previously, that's why the dot worked so well, but still I feel like I should have mentioned it. And now with that in mind, we can safely move on to the mechanical. And for the mechanical, there, well, aren't really that many mechanical components in our controller. I mean, the main one is the joystick, and that's kind of already pre-assembled. But there are still some important things to note, and that's how are we gonna attach everything? And the answer to that is these circles on the corners. Basic idea is simple. We'll just start with a cube, we will flatten it, change the proportions, remove the middle to make space for the pins, and add the holes in the corners like so. Now we can just pop the screws into all of these and attach, for example, the joystick. And this may seem like a fairly simple process, but man, did it take some serious trial and error, and I mean trial and error, for the matrix as well, and then for another component I didn't even end up using. Each one of these is me remeasuring, remodeling, reprinting, remeasuring, remodeling, reprinting, and so on and so forth, but there we have it. Now we can print things for those components that will hold them in place. And you wouldn't believe it, but next there is the design, where we can use those things to design the final controller. And now I know that I've been rushing like crazy these past couple of chapters, but almost all of the interesting things in this project were in the planning, coding and electronics phase. So electricity and mechanical were kind of meh, but the design part is where it gets surprisingly interesting. That's because for the design you might think that we're mostly going with looks or style, because that's what it sounds like, and like, yeah, style would be a concern, but that would be a concern number 4. The actual goal that I'd be going with is utility, feasibility, assembly, and only then the style. So what do I mean by all those? Well, first, utility is simple enough. We want our design to be usable. Yeah, I mean, that's simple enough. Next, feasibility. That's because as nice as it would be to have our controller be made out of indestructible nuclear pasta forged at the core of a dinosaur, unfortunately our show's budget doesn't really cover that, so we'll need to temper our expectations. Next, the assembly. That's because we don't really have access to the Iron Man tech that just creates the whole thing from scratch, which means that we'll need to plan accordingly and mind the physical restrictions of our universe in a way that will allow us to later on assemble it with no problems. That's a foreshadowing. And only then the style, which I don't really care about in this case, to be honest. I mean, in the future, style will be a concern. I still want things to look nice, you know, it's important, but nah, not today. And so with that in mind, let's begin with a cube. As always, we take the cube, flatten it, and change the proportions. Now we'll just cut out the circle for the joystick, and the square for the 8x8. This will be the face, where we'll use the joystick and the matrix. Next, we'd add some places for the screws on the corners to attach it, and some supports for the 8x8 and the joystick. That's because we don't want them to fall completely into the holes, only we want them to be in the right position, so that's why we need those supports. Now next, I will actually move the screws to the corners and remove the joystick support for a reason that I'll explain in a second, and there, we've got the face. Next is time for the walls. We start by adding them with the edges with a thickness of 2mm. Then in order to attach it somehow, we add these rectangles with holes at the bottom. This is how we'll slide them together in order to attach the screws. Great! Now we've got our sides to connect the face. Now it's time to attach the matrix and joystick to them. And we'll do it by adding these support beams. They will hold our parts in place using the screws on the corners. And there we go. Cool. So that's the basic idea for utility. Because this would work as our controller, but there is still 2 more requirements to hit. First of all, what will we make our controller of? Well, there are many options. In this case, the main regulator is, unfortunately and boringly, our budget. So on a spectrum, with the lowest being cardboard and the highest being whatever they build the newest colliders out of, we land on the cardboard. Okay, I'm really not famous. I'm really not, so unfortunately I can't really afford to do much. And that's why... Oh, wait, what's that? What was that here? Hold on, it's the... Oh, we just got the last minute appearance! It's the Patreons! Bringing us up to the 3D printed. This is my 3D printer. Their name is Jesse, and I bought it specifically for occasions like these when I need to make something for a video. And I bought it because of my Patreons. Thank you, my beloved patrons. And so now that we have our best feasible option for the material picked, we need to talk about the problems and the upsides. The upsides are obvious. I can just make a 3D model and then print it, which, considering how many 3D animations I use in my videos, well, let's just say that works pretty well with my skill set. But there is a downside, however, and that downside works like this. Imagine that you have a shape you'd like to print. The way you print it is the printer starts at the bottom and it's going up and up and up until it's printed. Simple. But there is a pickle, because imagine that to this shape I had a cylinder with a ball at the end. Now if we try to print the shape, it will work just fine, until you reach this point, where you will have a flying shape in the sky, and that shape will fall on the ground. Now this problem isn't unfixable, and you could just add some supports like this, and then yeah, it's completely printable, you can easily detach the supports, but we won't be dealing with that, it has its own problems. And instead, one thing you might notice is that if you take this cover and the sides, flip the sides upside down, then you can see that there are no hanging parts. That's why I switched from the screws on the floor to the screws on the sides. That's because with the screws on the floor, I need to have the screws connector on the bottom and screws connector on the top, which would lead to a hanging part. And there we go, we've gotten through 2 pieces. Now we move on to the third. How we're going to assemble it. And there are certain pickles there. Unfortunately, we can't use any fancy components, any specialized tools, no custom PCBs. We're just gonna have to do it make it style, with just random stuff around my office. And speaking of that, and so there we go. We've reached the assembly. Now all there is to do is just combine all the parts we spent such a long time designing, run the code, solder the wires, and get everything finished. And by now you gotta know I'm just gonna hit you with a time lapse like... Okay, let's test this. It's done! And so there we go. There we have it. It's finished. The back does look terrible, I know, but it worked. Past tense because I broke it already. But I am still satisfied with this. That's because this was meant to be for learning. And I have learned a lesson. The reason why this is so terrible is because I just went with wires. I went with general parts that I just had lying around the office to make this mess. If instead, however, I designed a PCB board and then had it delivered, this would have been so much cleaner. I could have added a little neat thing at the back, maybe even added the batteries. However, I rushed it. Big mistake. But still, I shouldn't have rushed it. Designing a PCB isn't that difficult. I have done it in the past. I've done it in the past for a video, and yet I chose this approach for some reason. But the important thing is that it worked, and it's actually a lot cleaner than it seems. All the parts that I actually put into the design are really solid. It holds up really well. There are the screws, which means that if I wanted to, I could actually dismantle it, if not for the cables. And it worked. It's easy, convenient to use. The basic idea turned out exactly like the finished thing worked. And honestly, I'm kind of proud of this. It has that make it charm to it, you know? Beauty at the front, absolute mess at the back. And so with that in mind, there's actually someone I would like to show this to. A friend of mine, Tefta. Among other things, Tefta makes open source hardware and software for prosthetics like these, and basically, whenever I have a question about electronics and, you know, designing things, I always go to Tefta because he's the expert on the topic. And so I just thought we could call him up real quick.
Oh, hi, Make It. How's it going?
Hi, Tefta. Hi. Yeah, so basically I made this thing, and
Oh, that's
I want to
cool.
show it
You
to you
know,
because
I actually
it's
wanted
like,
to show you something real quick too. I was actually just finishing up one of my hand projects, so it's kind of cool, but I still have to work on the bracelet and other things, but it's cool nonetheless. But yeah, anyways, what do you got to show me?
why do I even try, honestly? Don't worry, it's broken. I broke it a long time ago, it's fine. That turned out better than expected, didn't it? Well, to me, I honestly didn't think it would work at all. So the fact that it worked, that's already a tremendous success. I really hope you liked the video. I really hope you like the practical stuff as well. And this is the thinking segment, in which I would like to first thank All Matter for this. It's gorgeous. It's lovely. I love these. Both of these as well. I never in real life have looked as good as in any of All Matter's creations. So All Matter, I have nothing to give you, but you keep making these things. I just want to say thank you. Truly, look at how amazing them are. Someone else I would like to thank you is my Patreons, especially Acronymus Useless Quasar Legbear and recently Timon. Hi Timon, welcome to the higher up tiers. I would like to thank you all for being the highest tiered Patreon supporters. Thank you so much, thank you to all of my patrons as well, because I really wouldn't be able to make this video if it wasn't for your support. And like, yeah, it's kind of easy to point out the obvious support, like for example, I don't know, I got a 3D printer in order to print stuff for videos, but my laptop broke as well, and I was able to buy this ThinkPad for $100 from Patreon money. Also, this apartment that I'm currently in, I'm renting it using Patreon money. So I would like to thank you all not only for supporting me with getting things for these videos, like from hardware through tools, but also for just supporting me surviving. I really wouldn't be able to rent a apartment without you. Now we just need to finish off the video with the usual. I stream every single day for charity. It's a series of live streams called Charity Checkups, which I have been streaming every single day for the past almost 800 days, okay? 800. This is a cry for help. And I have a Patreon, I have a Discord. You can donate to charity, it's great. And for now, I think that's it. I do have to unfortunately go now to make more videos. I'll be making them on these live streams. Oh boy, how isn't that fun? And for now, I suppose that'll be it. Thank you everyone so much for watching and have a great day. Bye.